Hello. Today I want to show you kind of a fun puzzle that has to do with the table process of multiplying. If you haven't seen how to multiply polynomials together by using a table, you might want to watch that video a second. But once you've done that, they really open up a bunch of different types of puzzles that can be done with that. These puzzles really serve no purpose necessarily in and of themselves, but they do really help you to think about a bunch of different properties and try to keep them straight. And variations of these puzzles could be used to do specific math problems like dividing polynomials or factoring polynomials, which is why I usually teach it to my students. So down below is a couple different examples of table puzzles, and the goal in each one is to take what's been given. Here I've got a little bit of the work in this problem, and I want to figure out what was the original question that was multiplied. That's the stuff on the edges. And then what is my final answer? Here I've got different combinations of things, and here another different combination of things. And so let's see if we can answer this and figure out what was the original question and the final answer. Now, some properties that these table puzzles have, and in fact any multiplication table has, is that if you, well, first of all, just to get from the outsides into the table, you multiply. So this times this has to be x squared, and this times this has to be 12x, and so forth. Another part is that the answer comes from combining like terms, and in these multiplication tables, like terms are almost always lined up along these diagonals. So this diagonal, which is just this one box, is the x squared, and this diagonal adds up to give us this x's term, and this diagonal is this number. Another property of all these is that rows tend to have common factors, which a lot of times we can pull out. And columns have common factors that we can pull out. And then the last property is probably the most, I think, magical, the least intuitive, but one of the most powerful properties that we have, and that is that the diagonals in these multiplication tables, so what I mean by that is this diagonal here, if I multiply them together, that has to equal what this diagonal multiplies up to. So, as a quick example, this is true even in elementary school with the old elementary, the old multiplication tables you might have learned. If you take any section of this table, even this first example, if I multiply these two together, 2 times 2 is 4. And if you multiply these two together, 1 times 4 is 4. Here, 8 times 15 equals 120, and 12 times 10 is 120. And you can do other combinations. You could do this long diagonal, or all the way down to 25. So 1 times 4 times 9 is 36. 3 times 4 is 12, times 3 is also 36. And they don't necessarily even have to be pure diagonals like this. If I were to maybe look at a rectangle and just look at opposite corners, 2 and 15, when I multiply those together, I get 30. And 3 times 10, if I multiply those together, I get 30. And so that's true with just numbers in these tables, but it's also true in these polynomial multiplication tables. So how can we use these properties to answer this question? Well, maybe I can start here. I knew this diagonal has to equal the same thing that this diagonal equals when we multiply them together. So this is 24x squared. This has to be 24x squared, and the only way that can happen is if this is a 2x. So 2x times 12x is 24x squared, and so is this. Now I know all of the work, and it's pretty short to figure out what the question originally was and what the final answer is. To figure out what the final answer is, we just combine like terms. The final answer is x squared, and then these two things added together are 14x's. and then 24. And the original question is, I always start by looking at the top row and pulling out any common factors they have. They both are divisible by x, so I'll start by pulling out an x. And once I've done that, the rest of these are determined for me. If this is x, this has to be x because of multiplication. And if this is x, this has to be 12. 12 times x is 12x. And if this is 12, then this has to be a 2, because 2 times 12 is 24. And notice this last box also matches 2x is 2x. So the original question might have been x plus 2 times x plus 12. And our final ultimate answer is x squared plus 14x plus 24. And just as a reminder, if you haven't checked your work with any of these in a while, it might be useful to see that done on a calculator. If you have a TI-83 or TI-84, you can check these very easily. Type in the question, so x plus 2 and times x plus 12, and for me, I get 119. That's because my x is currently the number 5. You might get some other random number. That's okay. In fact, the randomer the better. And now I'm going to check my answer by typing in x squared plus 14x plus 24. And if all worked out, I should get 119 back again, which I do. Since the answer I got here when I plugged it in and the answer I got when I plugged in the answer match, that means these expressions were equal. So here's a few other examples. Let's walk through the logic that's required to solve these. So 12x squared, this, if I know either the first or the last term in my answer, those always go in these opposite corners, so I could immediately write 12x squared here if I want. I don't know the answer, the number part of the answer, so I can't fill that in yet. But I do know that the x's, so this diagonal, has to add up to 11 x's, and so I could write that this has to be 8 x's and 3 x's, add up to 11. And at this point, I could figure out what this is, and I think solve and find the rest of these and find it that way. Or I could use the cross-multiplying technique. 8x times 3x has to be the same thing as 12x squared times this. So I just did that in my head. This is 24x squared, and so this has to be 24, so this has to be a 2. 2 times 12 is 24. And if that's a 2, then this has to be a 1, because 1 times 2 is 2, and 1 times 3x is 3x's, and then this must have been a 4x. And my answer was the 12x squared, the 11x, and this plus 2. And these table puzzles can be of any size. Sometimes I'll give even 3 by 3 multiplications, or I suppose you could give a 5 by 5 multiplication puzzle with various pieces here and so forth. The answer part, I almost know all of it. I can do 4x cubed. And then this plus 20 I can fill in over here. So if I know that this is 4x cubed, this has to be 4x squared. And this has to be 5x times x. This has to be 5x squared. And it looks like I might be stuck, but I do know that the x squared terms, so that's this diagonal, has to add up to 9x squared. And so the only way that can happen is if this is 4x squareds. 4x squareds and 5x squareds adds up to 9. And now it's pretty short order. This has to be a 1. And 1 times 20, this has to be a 20. And once you know the whole question, it's just a multiplication puzzle. X times 20, 20x's. This is 5x's. And this combines to 25x's. So there's a few examples of multiplication puzzles. I want to show you a division. This same sort of technique can be done to divide polynomials. Dividing polynomials is just a very specific type of table puzzle where you know all of the answer and part of the question, and you need to reason out what the other part of the question was. Dividing polynomials often can work out perfectly, but it doesn't always work out perfectly. Sometimes there's some remainders. And so what that means is that I can't assume that this 20 for sure goes here. Maybe this 20 is a little too much or not quite enough to what needs to go here. So when you're doing a division, it's important that you start with the x cubed term and kind of work your way across. In fact, usually when you're dividing, you're going to find that you do this sort of a pattern through the table, and that this number here at the end is the last number you know. If this number works out to 20 exactly, then you're good. This one worked out perfectly, and if it doesn't, then you've got to figure out how much of a remainder there is. Just like if I took, say, 119 and divided it by 4, that doesn't quite work out perfectly. It would have worked out perfectly if it was 116 over 4, but there's an extra 3, and so you might write something like 29 remainder 3, or 29 and 3/4, or if you use the calculator, 3/4 is 0.75. So just like you can do the dividing with numbers and it doesn't always work out, dividing polynomials doesn't always work out either. So the rest of this video is just 2 examples of that, so if you're interested, feel free to watch. If not, that's fine. Tune back in for another video as we use this same table technique to factor trinomials, and that's when you just know the answer and you don't know any part of the question, and you can still figure it out. That's pretty cool. So here's some division. Again, start with the highest power term and work your way across. This 12x cubed has to go here, and that means this has to be 6x squared. It's the only thing that will multiply up to 12x cubed. So 6x squared times 5 means this box has to be 30x squared. And then this diagonal adds up to 26. So a little weird here. The only way that this diagonal can add up to 26 is if this is something negative, specifically negative 4x squared. And if this is negative 4x squared, this would have to be negative 2x's. Negative 2 times positive 2 is negative 4. So negative 2 times 5 is negative 10x. Notice the pattern. I've kind of gone through, and next box will be this one. So I find that by realizing these two things are the x's diagonal. They have to add up to negative 2. So this has to be positive, I think, 8x's. Yep. Negative 10 and positive 8 add up to negative 2. So this has to be a 4. And if this is 4, then 4 times 5 is 20. And that's exactly what it said it was. And so this one works out perfectly. This is your answer, 6x squared minus 2x plus 4. If you, or I have another example. The last example I'll do is what happens when they don't work out perfectly. So let's just attack it the same way. We don't know. It's not going to work out perfectly yet. So we'll start with 20x cubed here, which means this is 5x squared. 5 times 5 is 25x squared, and so this x squared diagonal has to add up to negative 11. It means this has to be a pretty significant negative number, 36x squared. So this has to be negative 9x's. And so negative 9 times 5 means this is negative 45x's. That means this diagonal has to add up to negative 5. I think I need positive 40x's here. So positive 40x's must have come from multiplying by 10. 10 times 4 is 40. 10 times 5 is 50. And notice that's not quite what was given to us. 50 is 3 short, so I've got an extra 3. And so you could possibly write remainder 3, but typically what's written is 5x squared minus 9x plus 10, and then you write as a fraction what's left. So plus 3 over the denominator. So instead of 3/4, we've got 3 over 4x plus 5. And typically in either Algebra 2 or I know in pre-calc, you study examples like this, where you've got an answer and then a leftover part, and those can produce interesting graphs and asymptotes and gaps in graphs and things like that. So typically for that reason, I think division is not usually done in algebra, but using a table, even Algebra 1 students can work out the logic behind this dividing. It's just an extension of the puzzles. So there you go. There's some table puzzles and specifically how to divide polynomials.